So now here the question is, the pigment responsible for the red color in the tomato has one functional group. The correct statements about this functional group is are. So this is your lycopene, okay? This molecule out here that you see is your lycopene. Now if you see the functionality present in the lycopene, obviously these are all alkene units present over here. So there is unsaturation, and obviously whenever there are these C double bond C bonds over here, so if you have a C double bond C unit, all right, and if you react that with obviously bromine, water, then obviously the products that you can think of to obtain via anti-addition of this bromine is going to be a dibromo compound, or there can be formation of over here the OBR unit. So both the dibromo and the bromohydrines can be formed over here. This particular lycopene unit is having no C double bond O functionality, so it does not go the reaction with 2,4-diphenyl 2,4-dinitrophenyl hydrazine to form the hydrazone. So this is not going to happen out here. Yes, it will be cleaved by an over here we will say by the ozone. So once you add ozone to this, cleavage will take at this double bond, and obviously it will, if you're using DMS with it, considering reductive ozonolysis, so obviously we will get the corresponding aldehydes over here. So we will say yes, it is going to decolorize, which is basically test for unsaturation. Okay, and this will help you to count. Okay, count the number of alkane units present. Okay, again it does not have any CHO group, so obviously it will not undergo any silver mirror test. So over here the answer will be A and C as the correct answers. All right, now next we have the question number 35, which is Hans synthesis of pyridine, and the options that are given over here, that Hans pyridine synthesis involves the steps. Some of those are aldol reaction, Darzin's reaction, Mannich reaction, and Michael addition reaction. So let's consider over here the entire mechanism for the synthesis of the pyridine using Hans process. So out here, first of all, we will take a beta ketoester, which is something like that. That will undergo reaction with the aldehyde in presence of the base ammonia. All right. So this is basically a condensation reaction taking place. So we will call it as a aldol condensation reaction out here in the first step. So obviously we will be thinking, so this is the alpha CH group that will condense with this carbon, removing water. So we will now think that this is the compound. Okay, neglecting the stereochemistry of the product formed, we will say this is what is formed over here. Now in the other step, okay, it is basically the R beta keto ester condensing with the ammonia, all right, and there is okay loss of water, so it's basically forming a imine type of a product. Okay, so that is what has now, these are the two things that are formed over here. We can think of tautomerization, and obviously we will convert this as NH2 and that to be taken as CO2 ET, and this is your R prime. Alright, once we have done that, let's arrange the compounds in a suitable manner so that we can show something how the reaction is taking place. Alright, so suppose I have my NH something like that. So suppose this is my second molecule which I'm writing over here initially. So this is my second molecule out here, and there goes my CO2 ET. I have written my first molecule out here. Alright, so this is my this one. Now think of doing a Michael type addition reaction wherein that proton is lost over here, making a C double bond N, and this is going to attack over here. So this is one position, two, and this is three, and this is four. So obviously this is undergoing a 1,4 addition reaction, and so we will say this is undergoing a Michael addition reaction. Okay, so that means out here obviously we will say aldol is happening and Michael is happening. So let's complete the whole process. We will say this is going to be NH. Okay, this is my R, obviously prime, I'm missing that. So this is CO2 ET. I have my double bond over here. This is my OH, that is my R to begin with, and that is my R. Isn't it so? Yeah, that is how what it is. Then we have my H. So this is also prime. And we will now do the tautomerization. Obviously, this is in the forward direction. So out here, I will say now, this is how it is going to tautomerize. This is my NH2, that is my double bond out here. Okay, that is my CO2 ET. There, I have my R, I have my H. Okay, just extending on the completion of the reaction. That is the whole idea out here. I could have left it over here, just thought that I should complete the reaction. Now, that if I say is losing water, so I'm meaning this oxygen is going to react with this particular nitrogen. So obviously this is going to form a imine type of a unit, isn't it? So if I do that, let's say we have this and we have that RH, we have the double bond out here, then this is the prime, that is the prime, that is the CO2 ET, we have the CO2 ET. At last, what is done is we have the Na, a oxidizing agent, which is HNO3, which is used over here. So finally, what will happen? That this R will come here, that R will come there, that will come there, and we have an N over here, and then we have the CO2 ET groups over here. Okay, so that is the entire mechanism for the Hans synthesis of pyridine, and I hope that clarifies the question that you had. And our answers are going to be aldol and Michael reaction. And I have segregated the steps where the aldol is happening and where the Michael is happening in this reaction over here. Okay. Thanks for listening. Keep visiting Saurabh's classes. Okay. Have a great day.